Virtual Academy students, this is Ms. McCauley, and I'm going to give you some extra help on the Honors Chemistry Stoichiometry problem. This is probably one of the toughest problems you're going to have, so it's really important that you spend some extra time making sure you understand this, especially if you want to go on to AP Chem. So I've posted some extra resources in the Virtual Academy Open Office Hours page. So if you go to Classwork, and then scroll down to Math, or Science, click on Chemistry, and I have linked an Honors Chem Stoichiometry Google Doc for you. So these stoichiometry problems are tricky. There's lots of steps, and there's an easier way to tackle them than the way that's presented in the module. In class, we solve these using something called a Bca Table. So I really recommend that you click on this link and explore the Chapter 9 resources that we have. So when you click on that, it's going to pull up all of the material we normally use in class. So first thing is, I want you to open up those Chapter 9 notes. And this goes through and just gives you a different perspective on how to solve stoichiometry problems. So the main idea is that this is really like baking a batch of brownies. So if you're making brownies and you want to have a single, a double, a triple, or a quadruple batch, it's all about the ratio, how many ingredients you have and how many brownies, how many products you can get out of it. So that's how the notes start. And if you click back here, we have a lecture video of either me or Mrs. Vandewally going through and explaining each step. So if you click on that, it's going to pull up and we'll actually go through and do all those problems with you. Okay, so do take some time to go through that. So if we set this up with a Bca table, we look at before the reaction, before the change, what do we have? During the change, so that means like when we're taking the brownie batter and putting it in the oven and making finished brownies, and then we have after, what we're left with when we're done. So before the reaction, we have brownie mix, water, oil, eggs. During the change, we're converting that via chemical reactions in the oven, so that afterwards we have delicious cooked brownies. Okay, some key vocab. Excess means excess, left over, there's more than enough of something. And as you go through these problems, it will really help. One important note is that you can only ever have moles in the Bca table. Okay, so you have to have everything in moles. If you're given something else, you've got to first convert into moles and put that into your table. And if you want a different answer, you have to take the moles out of the table and convert. Okay, so let's take a look at this problem. You're going to need a periodic table, a calculator, and some scratch paper. I wouldn't try and type this. It's going to be really challenging. Okay, we have two problem types here, A and B. Let's just only focus on A. So it says how many moles of CO2 will be produced if 9 moles of oxygen completely react. So when we look at this problem, they give us the balanced equation already. This is like my recipe. Okay, these are my directions, and it's giving me all the ratios that I need. The coefficients in front, that's what we're pulling our ratios from. Remember, if there is no coefficient, we just assume that it's 1. And I'm going to try and color coordinate this so you can follow the variables as they move through. So let me mask part of the screen here. And let's just analyze what we have before the reaction, what's going on during the change, and what we have after the reaction. Okay, so on the left, these are my reactants. This is what I start with. And on the right, these are my products, what's produced, what's made after the reaction is, oh, I wrote produced instead of products. Okay, so before the reaction takes place, what do we have? Okay, what will be produced if we have 9 moles of O2? So let's start with what we know. We know that there are 9 moles of O2. Before the reaction, I already messed up my color coordinating. Let's fix that. 9 moles of O2, and we're trying to find the CO2. There, so CO2 is going to be in blue and oxygen is going to be in red. So before the reaction starts, we have 9 moles of oxygen. Okay, now, kind of silly question. Before you make brownies, do you have brownies? No. So before the reaction starts, do you have any products? No. So before the reaction starts, we don't have any CO2, we don't have any water. But the question to ask ourselves is, okay, well, like how much of the other stuff do I have? The problem tells you that the oxygen completely reacts. So that means that all 9 of this is going to be used up. So how much of this C2H5OH, this hydrocarbon, do I have? I have enough. I have enough that I completely use this up. Does it matter how much I have? No, not really. We have enough. We're going to just call that excess. There is enough left over. Okay, so I'm hoping that you're with me here. If not, pause the video, go back, try and get with me on this step. So before the reaction, I have exactly 9 moles of O2. There's enough of this, and nothing's been produced yet. Now, during the change, during the actual process of the chemical reaction, I am going to be using up, subtracting the hydrocarbon. I'm going to be using up the oxygen, and I'm going to be creating some amount of CO2 and creating some amount of water. So the next question we've got to ask ourselves is, what am I going to run out of first? 9 moles of oxygen or more than enough hydrocarbon? You got it. We're going to run out exactly of those 9 moles of oxygen. So during the change, I am using up exactly 9 moles of oxygen. And how much will be left when I'm done? You got it, 0. There will be 0 moles of O2 of oxygen left when we're done. Okay. Now we're going to fill out the whole table, even though it doesn't ask you to, just so you can understand the process. So this is my limiting reactant right here. Okay, this is what I'm using up. This is LR, limiting reactant. And this is excess, my excess reactant. So everything I'm going to do is going to be based off this 9 moles of oxygen. So how much hydrocarbon did I actually need? I needed 9 moles of oxygen times the ratio of the unknown to the known. Now that's probably new. Go back to the mole ratio section of those lecture videos. But I'm going to try and show you a simple trick with just the color coding. Right now I've got 9 for oxygen, and I want to cancel that. So I want to end up with moles of my hydrocarbon. So I'm going to go up to these coefficients up here, the ratio of the unknown to the known. So for every 1 mole of the hydrocarbon, I need 3 moles of the oxygen. Do you see how that red cancels out now? 9 moles of oxygen times the ratio of that. Okay, so if I have a lot of this and I use up exactly this much, how much did I need? I need 9 divided by 3. I actually needed 3 moles of that hydrocarbon. Now here's the kind of silly part. If you have enough and then you use 3, how much do you have left over? You've got extra, you have excess. So technically we still have excess left over here. This is like you kind of started with infinity, you used 3, and there's still a lot left. Problem didn't ask about this, but I want to really reinforce that mole ratio. Okay, so now let's apply that same thing over here to the products. So for CO2, how much am I going to create? Well, it's all based off my limiting reactant. I'm going to be creating 9 moles times the ratio of the unknown carbon dioxide to the known oxygen. Okay, so I'm pulling those mole ratios from the balanced chemical equation. So how much am I creating right here? Oops, let's see, let's keep that color coding consistent. So what's 9 times 2/3? Well, 9 divided by 3 is 3, times 2 is 6. So I had 0 CO2 before I started. I created 6 moles. How much am I ending up with? I'm ending up with 6 moles of CO2. Okay? Now how about the water? Let's fill out the whole table. Same thing. Everything's based off the oxygen that I'm running out of. So it's going to be 9 moles of oxygen times the ratio of the unknown water. So water is 3 moles in the reaction, and oxygen is 3 moles. So if we kind of take a look at this, what's 9 times 3 over 3? Well, that's 9. So what do I end up with? I end up with 9 moles of H2O. So that is how I solved that first problem. Let's take the mask off and look at it. How many moles of CO2 will be produced if 9 moles of oxygen completely react? Okay, so if I use up 9 moles of oxygen, I'm producing 6 moles of CO2. Now, for the next problem, it's trickier because they want grams, okay? So I'm going to go through and I'm going to erase my Bca table. Don't erase yours, just go through and start again below it. I just don't have room on this here. Okay. We're using the same equation. We're using the same recipe. But this time, Oxygen's not going to be my limiting reactant, okay? And this time, they also don't give me moles to start with. So let's set up the table again, and let's figure out what we know. I like to always draw a line to separate the reactants and the products. So let's just kind of start with what we know. We know that we are looking for some number of grams of the hydrocarbon. Now they want to know exactly how many are used up when this much oxygen reacts with this. Okay, so this time what's actually going to happen is we have exactly enough of each. So they're both going to run out. So before the reaction starts, I'm going to have some number of the hydrocarbon. This is what I'm trying to find out. And I'm going to figure out my moles of oxygen. I'm going to use it all up, and there's going to be none of that hydrocarbon left over. I'm going to have some number of moles of oxygen. I'm going to use it all up, and I'm going to have none left over. On this part, before the reaction starts, do I have any products? Before you bake brownies, do you have brownies? No. So before the reaction starts, you have no CO2. You're going to be creating some during the change, and you're going to have some positive number left over. Before the reaction starts, there's no water. You're going to create some, and you're going to have some positive number left over. Okay, so that's just the setup looking at the basics. Now, what's tricky is they give you grams. Only moles go in the periodic table. So we have to convert these from grams to moles. I put the molar masses here, but how did I get those? We just add up the masses from the periodic table. So don't just copy mine. I want you to actually practice this. Go to your periodic table, and for example, let's say we're looking at, I don't know, this CO2. You're going to take carbon's mass, which is 12.01, plus oxygen's mass, which is 16, plus oxygen's mass again. So CO2, that's really 12.01 plus 16 plus 16, so 32. That would be 44.01, and the units there are grams per mole. Okay, so then how do I actually get my moles? Let's go back to the table. So we have 6.25 grams of oxygen. So we're going to set up a little conversion. I'm going to sneak up here and write that out. So I messed up my color coding again. This is supposed to be red. Okay, 6.25 grams of O2. So if we have 6.25 grams of oxygen, I'm going to set up some equations here, some fractions. We want to get rid of grams, and we want to go to moles. From the periodic table, I know that 32, oh boy, I'm struggling. We want to get rid of grams. We want to go to moles. I know that 32 grams of oxygen make up 1 mole. So what am I doing? I'm taking 6.25, dividing by 32 to get my moles. So 6.25 grams divided by 32, 0.1953125. Now, don't round this number yet. Let's take like 3 or 4, so 0.1953. We'll take that many decimals, so 0.1953. This is how many moles of oxygen I have. So before the reaction starts, I have 0.1953. And if we look back at the problem, I'm using up exactly all of that. So I'm going to be using up 0.1953 moles of oxygen. It's all going to be gone. Now here's the part where you need to really focus and stick with me. How do we figure out how much of this was used up? It all comes back to the ratio. So I'm going to be using up 0.1953 moles of oxygen times the ratio of the unknown hydrocarbon to the known oxygen. Okay, so what am I really doing here? I'm just dividing it by 3. So let's take that same number in our calculator, keep all those digits, and we're just going to divide it by 3. So how much did I use up? I used up 0.0651. Now here's the question to ask yourself. If that's how much I used up, and I have none left over, how much did I start with? Well, that same number. What if it was 2? What if I used up 2 moles and there's none left over? How much did I start with? 2. So since these both exactly reacted completely, what you used up, that's what you started with. So let's plug this number in here. This is my beginning amount, 0.065, 0.065, and we'll just truncate here, 51. Okay, that's good enough. Okay, so we've done the hard part. This is how many moles you had to use. But what's the problem? Ugh, they want grams. Now, we don't really need to fill this in, so I'm just going to skip to this part. We have to convert that number to grams. So I'm going to sneak over here, 0.0651 grams of my hydrocarbon. I'm just going to put it over 1 to make it fractions. And now I'm going to get rid of grams, and I want my final answer to be in moles. So I go to my periodic table, I add 2 carbon, 5 hydrogen, 1 oxygen, and 1 more hydrogen, and I get a molar mass of 46.08 grams per mole. Now, what did I do here? I made a mistake. What did I do? This is 0.0651 moles. And what did I write? I wrote grams. This is wrong. Now, this is important. I made a mistake. You see my grams canceled out, but I didn't even have grams to start with. So when you get to this point, double check your work. Make sure you're not doing something silly, flip-flopping your units. Don't make silly mistakes like that. So I have 0.0651 moles. This is very important. Have those correct units. Put it over 1. See why this is important? It tells me what math operation I'm doing. I want to get rid of moles, and I want to go to grams. 1 mole is 46.08 grams. See how that flip-flopped my math operation? Before I was dividing, I should be multiplying. So we're going to take that same number that's in our calculator and multiply it by 46.08. And I get 3. Isn't that a nice even number? So I get 3. 3 grams. That's my final answer.